This meeting is being recorded.
In this video from Chapter 19, we're going to introduce this concept of standard reduction potentials. So let's take a look here. Reduction potentials, as noted, have been measured for many different electrodes. By that we mean different metals used as electrodes. So copper and zinc we've seen in the past, we've seen platinum electrodes. So these values have been measured and then tabulated. So we can't measure just the individual electrode potential. We can only measure a potential difference, and that's what we mean by they were tabulated. We assign a standard hydrogen electrode, the She here, to have a potential of 0. And then we determine the potential difference of everything else based on that. So by everything else, we mean all the other electrode materials. So let's take a look at this table below and see if we can start making some sense of this. So we know that we have oxidation and reduction reactions happening at the same time. We also know this term oxidizing and reducing agents. Based on the calculated cell potential here, the reduction cell potential, we can find some good oxidizing agents, some good reducing agents. So what we see here is that the most positive value here, these will be strong oxidizers. And that should kind of make sense. They will reduce themselves and oxidize something else. So we know the most electronegative atom here is fluorine. So that really wants to grab some electrons. So this will be one of the strongest oxidizers that we may encounter. On the other end, we can see down here, lithium, for example, is considered a very strong reducing agent. So strong reducing agents. Those are elements or species themselves that are oxidized. So we have strong reducing agent here. So something like lithium really wants to give up its electrons, and it would therefore reduce something else. So itself becomes oxidized, and it reduces something else. So that's good to remember when we're talking about reducing agents and oxidizing agents. Let's take a look a little bit above here. We see our table has a 0 value defined here for our hydrogen electrode. So this is our She. This is our standard hydrogen electrode. We define this as 0. So if we run another electrode, we can solve for that potential because we define the hydrogen as 0. So for an example here, say we had a zinc electrode at our anode, and then we had our hydrogen reduction potential at our cathode. We could solve for our cell potential using this equation where we have E of the cathode minus E of our anode, and we could plug in these values as is from our table here. So let's go up, let's see, zinc. There's zinc, it's negative 0.76. So we're going to use this value here, and then our 0 at our cathode. So at our anode, we would have minus negative 0.76, and here we would have 0. So our cell potential, if we use that standard hydrogen electrode and we measured or just our anode, we would get that our cell potential is plus 0.76. And we'll see that whenever we have a positive cell potential, that will indicate a spontaneous reaction. So we'll look at some other equations that will help us with this realization. And then also to note here, this standard hydrogen electrode reaction here, we're reducing 2 moles of H plus in 1 molar concentration by using 2 electrons to H2 gas. And since we're in standard conditions, we will be at 1 atmospheric pressure. So let's take a look at another example here. So say we have down below here, we'll see our our voltaic cell. Oh, there we go. So we'll see our voltaic cell here. And notice that we have, we've seen this in the past. We see our zinc anode, right? So that's going to be over here, our anode half cell, and we see that we have our oxidation reaction happening at the anode. And then on the other side, we see our reaction happening at our cathode. That's going to be our reduction. So we have oxidation at our anode, we have reduction at our cathode. So let's see if we can solve for the cell potential here. So we know that we have zinc and we have our hydrogen. So that's what we saw above. We saw this E cat minus E anode. And that's where we came up with our reduction potential at the cathode of 0 minus our reduction potential at the anode of negative 0.76. So this is where we saw that positive 0.76 volts. We should note that cell potential is the potential energy per unit charge. So we'll have this relationship, joule per coulomb equals a volt. And because of this, this is considered an intensive property. So it doesn't matter how much quantity we have, how many moles we have, this will be the same no matter what the quantity. So let's take a look here at sample exercise 6 and see if we can utilize the information provided in the table above. We're given our cell potential here as 3.21 volts. So that's going to be our overall cell potential for both of these half reactions. So we know that on this side, we're going to have our anode. We're going to have our cathode reaction over here. We have solid samarium as our electrode at the anode, right? This is our oxidation reaction. This will be our reduction. We have platinum here. Because the solid iodine is unable to establish that electrostatic potential. So we need an inert electrode over here. All right, so let's see. We know that our equation is E naught. We say naught when we write that little degree symbol. That tells us we're at standard conditions equals the E of the cat minus the E of the anode. So let's plug in some values here. We're given this overall, 3.21 volts, and we're going to set that equal to, if we look above on our table, or we can look up from another table, the reduction potential is listed as negative 0.54 for samarium, and that's volts, minus the anode potential here, the iodine is listed as 0.54. So we'll confirm that in our table. Here we go. So we have our positive 0.54. So that's for our cathode. And then our anode, that's what we're solving for. So we're solving for E anode. So what we do is we would take this negative value, or that positive value rather, because it was positive in the table. So we're going to subtract that from both sides. So I have 3.21 minus 0.54. So my anode is going to be equal to, my negative anode rather, is going to be equal to a positive 2.67. I'm going to divide both sides by -1 because I want the E anode, not the negative of that. So the result is that negative 2.67 is going to be the value under standard conditions for my samarium anode.